So last time we learned the absolute maximum and absolute minimum on the closed interval. And finally, we're getting into applications of the bacteria in drug use, building a fence and building a box, and so on. So we're going to have some very interesting lectures today and on Monday. Today more technical, but on Monday I will tell you why your eyeballs are spheres, why the FedEx boxes are cubes, why some trees are wider than others, and so on. That is what we call the optimization problems. So that's why we're teaching you this. We're teaching this to business majors, biologists, engineers, physicists. Everyone needs to know how to optimize things using derivatives. STEM majors. With the closed interval, it was different. We did find critical points, critical values. We listed them, and then we listed endpoints, because apparently a function can be maximized or minimized at the edges. So we had to plug them all into the original function and then compare the results. The biggest output gave me the absolute maximum, the biggest maximum from all the maximums. The smallest one, the smallest one. And this was the graph. The left edge gave me the global maximum, and then 2 points gave me global minimums on the floor. Let's do one more example and then move on to some nice applications of the drug use and bacteria. Thank you. I pushed this time, yeah. Surprisingly, I remember. So, let's find absolute extreme values on the closed interval. On a test, if you're afraid to forget, are we asking about local or absolute? If you see the interval, that is a closed interval problem, so that means usually we're asking about absolute values. Or else why would we put the interval there? The interval, so again, the domain of this cubic function is minus infinity and plus infinity. But we put a restriction on the domain from 0 to 3 for some reason. For example, that we only consider 3 people, or 3 months, or 3 days, and so on. Step 1, let's follow the steps and see if you remember them. So make sure you do. Don't postpone your homework. The moment you see absolute or local minimum maximum, they ask you to find a derivative. You find a derivative, 3x squared minus 3. Not too bad. Derivative done. Good. Critical values are the one that gives you 0 or d and e for the derivative. Quadratic functions don't have d and e, and in general, if you don't see a fraction, probably there's no d and e points. So we only need to find 0 points. 0 points will be coming from 3x squared minus 3 equals to 0. 3x squared equals to 3. Move 3 to the right. Divide by 3. X squared equals to 1. X is 1. Yes or no?
No.
Plus or minus 1, don't forget. A panda is crying somewhere if you forget a minus 1.
The negative 1 is not in the domain.
Well, that's a very good point, but that's the next step. So for now, you found 2 solutions, plus and minus 1 from the quadratic equation everywhere, right? On minus infinity to plus infinity. Bless you. This is the first step. So this is what you do. If you're already getting this idea, boom, half points on the exam are in front of you. Very convenient. But the new step shows up. The new step says, there may be infinitely many minimum and maximums, and maybe we're making a cut from here to here. You need to kick out the extras, if there are any. And we do have restriction from 0 to 3. So, step 2, get rid of the extras. X equals 1 and x equals minus 1. That's why I did not write them down. Are there critical values or not? Question mark. Should we keep both or kick something out? Negative 1 is not in a domain. If this is a real life problem, you're not supposed to include negative numbers anyways. So if this is a number of bricks you need to build a house, negative 1 is not in the domain. Not a critical value because of the restriction 0 and 3, right? And then x equals 1 is in the domain, so we can keep it. Step 3. Last step is the most fun one. You list all points, critical values, and endpoints. So no first derivative test, no second derivative test. You just make a list in any way you want. I'm organizing information my way. You can do it your way. It's very creative how people organize information. Just make sure it's correct. So there was one critical value, which is 1. And there were 2 endpoints, x equals 0 and x equals 3. These are 3 candidates for the global maximum, global minimum, between 0 and 3 and at the endpoints 0 and 3. How to find out if any of them give you maximum minimum? You plug them into the original function f of 1, f of 0, f of 3, and then choose the winner, the biggest output and the smallest output. Kinda, the idea makes sense to be honest, but let me know if it doesn't. So you choose this biggest output that gives you the biggest maximum. I don't remember the original function. Okay, here it is. X cubed minus 3x plus 4. If you plug 0, I think that's easy. It gives you 4 right away, yeah? The original function. If you plug 1, you will have 1 minus 3 plus 4. Original function, remember. What is that? 2. And then the hard one is 3.
27 minus 9.
3's cube. Yeah, 27. Minus 3 times 3 plus 4. Who knows? 22. Thank you. Good job. So we have 3. I will not put them in boxes because we don't need all 3. Choose the winner. What is the biggest number here? 22. Good job. So 22 is your global, the biggest one. Maximum out of all possible maximums, and it came out from the input 3. So you can answer there is a global maximum at 3,22. 3 is the location on the x-axis and 22 is how tall this mountain is. What is the smallest number in the list? 2. So that is my global minimum that came from the input 1. So that is global minimum, and the answer will be there is a global minimum point at 1, 2. And this is how you do these problems. This is a very typical free response problem, to be honest. So we usually give it as a free response, and we grade. We can see that you know how to take a derivative, how to find critical values, kick out something extra, and then check the endpoints and the critical values. Done. Questions about this? What do you think? This has lots of applications. You might be surprised, but I will give you one. The one I like was bacteria, and later I will show you some Harvard video about bacteria mutation and antibiotic-resistant bacteria. But for example, let's do this one and move on to something different. In your homework, you will be working with drugs. So the drug is decreasing in the patient's body. It's interesting to know when it reaches the maximum, what time it takes to decrease. I asked doctors because I was doing PhD connected to medicine, so I was invited to the morning walk with the doctors. So I asked them, do they know all these formulas and derivatives? They said that they have tools, computer programs, when they just can plug in inputs and it will give them the output using the formulas we're doing right now. But with experience of 30 years, the doctor knows approximately that this drug taking into account the weight of the patient, say 145 pounds, probably in 35 minutes the drug will stop working. So they know it approximately in their mind. That's a pretty cool idea, but it comes with experience. The number of the bacteria in a colony is given by the function n of t, number of the bacteria, so capital N. 1,000 is the initial value. So we start with 1,000 bacteria plus 30t squared minus t cubed. And then t is time. At time 0 we had 1,000. At time 1 we had 1,000 plus 30 minus 1, and so on. And let's say we timed for 25 minutes, from 0 to 25. When does the number of bacteria reach maximum, and what is that maximum? A very practical point, to be honest. So in a petri dish, it's very interesting that because the environment is finite, in a petri dish, you have those bacteria and they grow. At some point, they will reach the maximum population. And when there will be lack of resources, which is space and food, the population will start degrading. So the functions usually they do like so, look like so. Starting with the initial, jumps up because you gave them food in a petri dish and they have lots of space, so they don't have to fight for space, there's lots of space around. Then those are resources. Then they reach the edge of the resources and it starts slowly degrading and die out. So it makes sense to know when and what is the maximum. Let's see. It's exactly the same idea. Solution. The moment you see example and question about maximum or minimum, you start with taking the derivative, because derivative answers the question how fast and how much something changed. Does that make sense? F prime is 0 plus 60t minus 3t squared. Agree? Just take the derivative. We want to find zeros and d and e points. No d and e points in this case because it's a quadratic function, but we need to solve for zeros. So it's going to be 60t minus 3t squared equals to 0. Several ways to solve it. Which way would you prefer? Yes?
Or sorry, I think we're asking which way we prefer.
What did you want to say?
Because I think the most obvious way would be to factor out 3t.
Yeah, let's do that. I would definitely divide by 3, and then I would definitely factor out t. But you can also factor out 3t, but you could divide by 3 because there's 0, so it doesn't matter. 3t, we're going to have 20 minus t equals to 0. Product gives you 0, so we should just assume one or both give you zeros. T is 0 is one solution, and t is 20 is another solution. Put them in the box. And then I will say critical values, question mark? I don't know. Because it depends on the restriction of the domain. If I chose to only check from 0 to 10 minutes, I have to kick out 20. If I chose from 1 minute to 27 minutes, I have to kick out the 0 minute. So it depends on my own decision as a researcher, what the interval is. The interval was chosen from 0 to 25, so both are in the domain. Make sense? So usually students, they ask, where did 0 and 25 came from? And the dumb answer is, that came from the problem. The smart answer is, you as a scientist decide on that. So there's a group of scientists sitting at a table and they're like, what is the reasonable amount of time we should wait? Someone will say, let's wait for 3 days. And you're like, no, that's Thanksgiving is coming. I'm not gonna check the petri dish for 3 days. So that's like a whole, that's a joke, but there's a whole communication going on. Let's check for 24 hours. Too much, in 24 hours, they will be dead for quite a while already, the bacteria. Maybe 3 hours, maybe 25 minutes. And that's how people debate and they make this choice. Okay, the choice is made, so I'm making a list. Who can tell me what should go to the list? Well, those are t values in this case, but yeah, what kind of?
0.
T is 0. I heard what? 20. What else?
25.
Anything else?
Yeah, because 0 is included twice.
Yeah, 0 also mentioned here, but since we already found it as a critical point, we don't have to include it. So we have a list of 3 inputs. And we're plugging into the original function, which is not f, by the way, it's n. Number of bacteria at time 0, number of bacteria at time 20, and number of bacteria at time 25. We will calculate literally the number of bacteria, and we know by the theorem that the maximum or minimum can only occur at the critical point we found or at the end points. So there's nothing else to check. 0, 20 minutes, and 25. Apparently, there is nothing interesting between 0 and 20, and nothing interesting between 20 and 25. So that's why we're only checking those 3 points. How do I know that? Math told me this. Derivative should be 0 or d and e. Too much talking, let me just plug in. So I'm plugging into the original. N of 0 gives me what? 1,000. Because if you do remember, n was 1,000. That's the original number of bacteria when you just start looking at them. You also can decide on that, how many do you want to have at the beginning. Then at 20, I'm plugging 20 in, and I have calculations here. They give me 5,000. And at 25, I have 4125. Just like I told you, usually that is the prediction of the behavior. I do not know the answer actually, but I'm guessing as the biologist, which is part of my education, that bacteria number will grow, hit the maximum, understand that there is a limitation of the environment and resources, so they'll have to now fight for the resources and food, and then the population goes down because they also eat each other at some point and so on. So it makes sense that something in between there should be a maximum, and this is the maximum. Also, do you think it makes sense that the minimum was at the beginning? So 1,000 is a global minimum. They never ask us to find the global minimum because it's obviously going to be at the very beginning and at the very end. We started from 1,000, and if you really wait a long time, it probably will be 0 because they will all die without food. So that's kind of the idea. This is your global maximum. Since this is a real-life problem, you should kind of answer this in the scientifically intelligent way. So let's answer in a more beautiful way than we usually do, which is at time or when t is 20, what was it, minutes, so we waited for 20 minutes, that's my units. The number of bacteria reaches the maximum, reaches the global maximum. So let me put it in global maximum. What is the global maximum of, that's how you say it in English, in Russian we'll say in, I think, 5,000, what are the units? Bacteria. So very interesting, time is my input, number of bacteria. I like putting units in parentheses if you want to, but you don't have to. So units, bacteria is my input. No, time is my input in minutes. Bacteria is my output. Pretty cool. Yes?
Doesn't that mean that the bacteria will never actually, according to this formula, will never be out?
What? What do you mean?
Well, we only had 3 points at which, or 2 points at which we also only had 3 points that could be the minimum. And this would be true even if we had a larger graph.
Not necessary. With different functions, they have more wiggles.
Well, I mean, even on an infinitely large graph.
Oh, that's a very smart question.
It would still then we just ignore 25.
Yeah. He's right. Even on a larger interval, you would still get the same answer. And then I actually do have example.
And in fact, you'd never reach 0.
Like that. I do have example like this. Very interesting. Look at that. Whatever you're talking is about, you're actually asking about the limit. You don't know it, Chris. Whatever you're talking is about limiting position. So if you actually check the limit when t goes to infinity, which we did learn, that will tell you that it has a finite number at the infinitely amount of time you wait. That's exactly what you're talking about. You just might not guessing that. You're talking about limiting position at infinity. That's a pretty cool idea.
Wouldn't it go to negative infinity?
That's the thing. It will go to negative infinity, but it's outside of the domain. So you have to cut off at 0, because there's no negative number of bacteria. So you start with 1 grand, it reaches maximum, shrink to 0. It goes to minus infinity, but you know physically it's impossible. It's a pretty cool idea. So, let me think, should I show this example? Sometimes we just say, I'll show you this interesting example on the applicational problem. There will be more cool examples like this in 2.5. So let's have 2.5 and I'll show you more stuff. 2.5 is applicational problems, optimization problems. But the cool part of it, we're going to do exactly the same what we just did, just in the context of the some kind of cool ideas, like optimizing a box in FedEx, or building a fence, or the number of the drug, and so on. So one of my colleagues, he actually was doing optimization problem for his PhD, and he defended mathematical math biology model about the interesting case. You guys holding way too many phones today. You should stop getting distracted. So, the interesting case, when you find a patient on the floor on subconscious and then the patient got poisoned, and you can see it, you don't know how much the poison the patient consumed. So, he optimized what is the predicted number of the medicine we should give to that patient without knowing how much we should give. And that's kind of pretty cool idea. That's part of the optimization problems 2.5. Optimization problems teach you how to build a model. Many of you might become modelers, mathematical biology modelers, biological modelers, medical modelers. We have data science modelers. It's pretty cool. In this small class, we're going to teach, short class, we're going to teach you a model from 2 steps. We're going to have objective function. Well, they already said here. Objective function, I call it OF. Objective function, this is the one we want to optimize. Optimize. And the second one, we're going to have constraints. Constraints, which are just my restrictions. Like a domain, restrictions. Or maybe a limiting number of building materials, a limiting number of antibiotics you have in this particular hospital. So mathematical models, they are perfect. They say, you know what, if you have 1 million of vaccines in this country, everyone will be free from whatever disease we have. Practically speaking, it's impossible. We cannot create so many vaccines so fast, so many antibiotics so fast, so many pills so fast. And that's why constraints show up. They are either time constraints or resources constraints or something else. Constraint optimization problems are problems for which a function called objective function is to be minimized or maximized subject to constraints. Subject to constraints. So this will be a system of 2 things, objective function and constraints. Example, we're going to start with some kind of building fence. So your friend wants to build a fence at home with a given material of 2,400 feet long. So your friend went to the store and saw a sale for the fencing material, and on that sale bought without thinking 2,400 feet of materials. Now he has to use whatever he or she has. Build the rectangle fence with maximum area. Find the dimensions of the maximum area. Pretty cool idea, because you might not believe, but even though it already says it should be a rectangle, the rectangle can be looking like so. The rectangle can be looking like so, very thin. It may be this long, and many more. And all of these rectangles have different areas. That is interesting. Rectangle also can be a square, for you to know. Square is type of the rectangle where sides are the same. So areas will be different. That's a tricky part of it. And that is why with the given amount of material, you can choose the shape. Maybe you want a circle after all. You choose the shape. And if you don't choose a good shape, you're losing the space of your yard. That's a pretty interesting idea here. And that is why the shape of the desk you're sitting at is optimized. The shape of the screen you're looking at is optimized. The shape of this whiteboard was optimized by math. That's exactly what we're doing right now. Because they could do it taller or shorter. Well, taller is not necessary for people like me, so that they were particularly specific about that. But in general, there's some kind of idea behind optimization. So, what kind of area is the best? And the best in this case, maximum. Makes sense. He bought the material, he or she bought the material, I should say they bought the material. So what kind of shape will maximize the area, not to lose the size, the fencing shape? Not to have leftovers. So I will do, if this was just introduction, let's actually start building it. Step 1, sketch the picture. Sketch a picture. Whatever they tell you, sketch, this is, yeah. Much better. Sketch the picture.
Hold on.
Still, what?
There's no K in this.
Oh yeah, thank you.
There's a kid sketch.
Interesting.
What am I saying?
It depends on the week of the day when my English gets better or worse. Sketch. Yeah. It's like I told my other students, what did I tell in this class? It was funny. The clock was tickling? Like what? And they told me the clock is tickling. That was funny. No, but sometimes I say funny stuff. So sketch a picture. We have a fence. Let's make a very general, not too thin, not too thick, and not a square, rectangle. Area of this rectangle is unknown. But we do know, and it's called sizes X or Y. We like calling it lengths and widths. So as a modeler or scientist, STEM major scientist, and you guys chose STEM majors, so you have to be precise about this. You need to name everything nicely. Let L be lengths. And sometimes we even require units. What are units? Feet, right? Because it was given in feet. W is widths. Widths. Also in feet. Area is area. Do we know the formula, the mass representation of the area? So that's where the modeler comes in and they get into the circle, and then the designer sketches the graph, someone lists the variables, the person who is in charge of finances tells you, okay, we already have 2400s, let's not buy anything more. And then they all look at you, at the person who took calculus class, and they're like, what is the formula for A? And we don't remember it. So do you remember? What was it? Yeah, length times width. So that's where your education comes in. You're not going to be paid 6 digits for something you can Google, okay? You can Google this formula, but you're supposed to understand what is happening. We're building something that has area. It's a shape of the rectangle. There is a formula L times W for this area. So these things we listed. Now there's also some kind of number 2400s. That is interesting. As a mathematician or a modeler, you're supposed to know what it means, those 2400 feet. So what do you think it means, particularly from a mathematical point of view? I will make a hint before someone answers. 2400 is the material they bought, right? So you as a friend shows up and says, let's measure. We're going to put like a stick or a node here and start walking and putting the material. Material. Let's turn to the left, material, turn down, material, turn down. And you hope you're not gonna like have a gap, or else your friend will think you're dumb. Like, you're supposed to know how to do this. You took calculus class. Hopefully, you're also not gonna have a sticking out edge. That means you wasted the material. So your goal is to finish where you started. What is that from a mathematical point of view? What?
Area equal to 4.
What's the name of that? Perimeter. And the circle perimeter will be for a circle. Good job. So the length of this rope that creates a shape is called perimeter. For a circle, it's circumference. For the rectangle or square, it's perimeter. For the 3D shape, if I'm holding a soccer ball, football ball, okay? Football ball. So a soccer ball. Then the outside shape will be also a material, right? Called surface. So that's what we teach in calculus 3 class, surface. So that material that surrounds something. That is called P. And let me put it here. Perimeter P. Now, the most interesting part starts now. When you finish listing, okay, let me write down perimeter. The most interesting part starts now when you finally build the model. The model should have 2 things. Objective function, that's the one we need to optimize. Optimize is minimize or maximize. And constraints, the restrictions, which are usually coming from the amount of material, time, or some biological meaning. So we're going to have a system. The first equation is my objective function. What do we need to optimize here? Do you remember what we're doing? What are we optimizing? Area. Area, which is length times width, is my objective function. And specifically, we want to maximize it. Sometimes we want to minimize something. For example, cost of the smartphone. Or we want to minimize the cost. We want to minimize the size. So there's a very interesting optimization problem of the minimization of the things we shoot into space, because it's hard because of the gravity, it's hard how much they weigh. So do you know that origami recently was used, mathematical models of origami, to fold metal so nicely that you can ship it to space and then it will unfold? That's also optimization problem. That's pretty cool. So some things should be minimized as well. This one should be maximized. The constraints are coming from this number. There's not more material than 2400 feet, you like it or not. So P, which is the perimeter, what is the formula for the perimeter?
2L plus 2W.
2L plus 2W. How do we know that? Let's see. This size is W. Let's add it to L. W plus L plus one more W plus one more L. So double each side, and you will have a perimeter. So you're literally walking and you're measuring the material. That is 2400. That is my constraints. This is called a model. Number 2. This is called a model. Has objective function and constraints. So this is your first experience in your life to build a model. Some universities have actually a class called modeling. And they teach you or try to see if you have imagination to model the size of the screen on your smartphone and optimize that. Or something like different. So it depends. Finally, so we have this, we have a picture. The next idea is to maximize A. We know this word, maximization or minimization. We need to take derivative of A and set it equal to 0 in D and E. That's exactly what we just did today and yesterday, day before that, and so on. But A has two variables, length and width. Those are variables. We don't know how to differentiate things with more than one variable until we get to calculus 3 class, which is called multivariable calculus. Thus, it would be nice to get rid of one of the variables. To do that, you use equation number 2. I'll put it in the box. Use. So let's do like this. Step 1, sketch a picture. Step 2, build a model. So writing down all the variables. Step 3, use equation number 2, which are constraints, to solve. Not today is my English just stopped. To solve for one of the variables. Vars are variables usually. Doesn't matter which one, choose the one it's easier to do. In this case, they're both the same. 2L plus 2W equals 2400. Let's choose to solve for W, for example. I don't know, doesn't really matter. The answer will be the same. Let's divide by 2. It will be L plus W, 1200. V is VW, yes, thank you. Double V, right? Minus L. Yeah, let me see. Oh, that's you just thinking how it's going to be. Yeah. So put this in the box because we will need it. This is a correlation between two variables you created, width and length. Apparently, they have restrictions. As you can see, L cannot be infinitely big. L cannot be 5,000. If length of this rectangle is this long and exceeds 1,200, says 3 grams, then there will be no space for width. Moreover, width becomes negative. If length is exactly 1,200, there will be 0 width. So it's not a fencing anymore, it's just a line. If L is, say, 900, then there will be very small size left for width, and so on. And that's where the choice comes in. What is the optimal choice for length or width to have the optimal area? But now you can see there is a domain. Length not only should be positive, or else it doesn't make sense to have negative, but it also should not be What do you think the number? I actually just said something, but maybe you have different ideas on that. Is it 1200 or 600 actually? Do you know why? Because we need to go one way and then another way. So 1200 will be just one way. But even 600 is already not good. If I have 600 here and 600 here, together it's 1200. 12 minus 12 is 0. So there will be no space for the widths left.
Wait, I thought we're going from 24 in the first place. Therefore, 1200.
And we already divide by 2, so we got rid of.
Adding 2 out, won't we?
Still. The math shows, you see, 1200 is the number.
So it shouldn't be equal, it should be less.
Less than 12.
Yeah. Or else it will be just one length or one width, and that is not. The area is 0 because if one of the variables is 0, the area is 0.
It would be less than 1200, right?
So that is domain. Yeah, 1200. So that is domain. No, less than 600.
I don't understand.
Let's see. I see your point.
Because
Yeah, let's fix to 1200. 600 is coming from. Oh, I will tell you later where the 600.
duplicated the math.
Yeah. I'm overcomplicating it. So, good point. Finally, let's take the derivative. Let's plug in step 4. Step 4. Plug into objective function 1. Okay, my objective function was area. Area was width times length. I just solved for the relationship between W and L, so it's going to be 1200 minus L times L. Now it's a function of one variable and we know how to differentiate that. Maybe even distribute, not to deal with product rule, and put it in the box. This is my new formula for the area, which only depends on length now. And we will be differentiating this. So finally we get it. This is not calculus. So until now we did not do any calculus, to be honest. We built the model and just did some algebra. Now calculus starts. 5. Now this is why you are learning this, because differentiation is part of the calculus class. To maximize, you need to maximize A. You need to take a derivative of A. Derivative of A is 1200 minus 2L. 2 goes down, L to the 1. You need to set this equal to 0 or D and E. We don't expect to have D and E stuff in applied math, in applied problems, so. Let's solve it. 1200 equals to L. L is 600. That's where I got 600 from. 600. This is the only critical. Well, first of all, you have to check the domain. It is in a domain. It's not negative or something. So there are no other critical points here. We can actually check it using the first derivative test. We can put 600 on the sine line of A prime. And if we expect that we are looking for maximum area, what kind of signs do we expect to have for the derivative? Minus, minus, plus, plus, minus, plus, plus, minus. Therefore, minus, plus. Yeah, I would say plus, minus. So from your point of view, if we expect to have maximum, I was thinking it should be positive first to increase, and then negative to decrease to have this peak of the mountain. So if you check, definitely don't go outside of the domain. So actually it is from 0 to 1200. Check some test points and you will see it's plus and minus go up, go down. So it is maximum. Since there is no other critical points, we can claim that this is not just local maximum, it is a global maximum as well, because there's no other places to go. So L equals 600.
Technically, wouldn't we have to test for the maximums as well, for the boundaries as well?
For the endpoints?
Oh wait, there's no endpoints. That's not right.
Domain will be your endpoints. It's a good question you're asking. Some professors teach you this way, that you have to check endpoints. It's too slow. So I usually try to explain this way. There was only one critical point. On the endpoints, you know your fence does not exist. Your fence will be just a line, either only width or only length. So there's no area. Thus, there's only one minimum or maximum, something in between. 600 is your answer since there is no other critical values. 600 is my global maximum. It's local by the first derivative test, but it's global from this claim. There's no other critical value, so it cannot go and change direction and have one more hill anymore. Finally, let's calculate the final answer. And I'm kind of done. As you can see, these problems are time consuming, but modeling is time consuming. That's why people get masters and PhDs in these problems. This is like basic stuff. So last step, step 6, find whatever we need. If L is 600, W is what?
600.
Let's see, where's my box for W? Here it is, 1200 minus L. 1200 minus L, which is also 600. That is a coincidence that they are the same, so it's not always the case. Finally, your area. They ask us, your friend asking, so what will be the area, excuse me? And you'll be like, oh, I found it. It's L times W, which is 360000. What are the units? If these are feet and these are feet, this will be feet times feet, which you're correct, feet squared. This is the maximum area with the dimensions of the rectangle being 600 by 600. What kind of rectangle is that?
Square.
It's a square. Which makes sense, and that's why I have those funny pictures over here for you. What is the perfect shape that nature creates for your eyeball? It's almost perfect sphere. Spheres and squares and circles are perfect shapes with which can accumulate the biggest amount of stuff in it, unless there are extreme additional constraints. That's why your eyeball is almost a perfect sphere. That's why windows are usually squares, but when you see the windows in our buildings, they are usually tall rectangles. Guess why? They're easier to open. In old times, they were squares, actually. And they have more light from the top to bottom.
And it's also why bubbles are round.
This should be a square, but then I will not reach the top. And that's why they made it longer and shorter. The width became shorter. Your smartphone should be a square, but it will be hard to hold. So the ratio of the smartphone and the TV screens were calculated a long time ago, and they have optimal ratios. The half of the sphere is a ladybug. That is a perfect shape from the nature as well. The perfect shapes of trees are coming from where the tree is growing. If the tree is growing in the forest, then the popular shapes are like apple trees. They collect the optimal amount of light. Some of the trees try to protect themselves from mosquitoes and bed bugs, so they have pointy edges. And some trees are growing on the top of the canyons, like Grand Canyon. They learn to even optimize the shape of the trunk and trees in general, creating spirals, which we call helix, and we study them in Calculus 3 class, like D&E spiral, DNA, not DNA. DNA spiral is also a biological optimization. It can hold the maximum amount of information while spiraling up. The basic aerodynamics has very nice examples how the wings were created so that the wind goes through by not crashing the plane, but supporting it from the sides. That's the aerodynamics example as well. I think, what other examples you can think about? What is the optimal examples we have? I always like to say the watch on my hand and the watch you see on the wall are circles, because you want to see the most on your hand. The tables and the piece of paper you're holding. For you to know, the piece of paper in America is not the same as the piece of paper size in Europe. We have different sizes, which called A4 and letter size. So optimization did not match between countries here. And so on. Think about more examples. I will ask you on Monday. What else do you think is optimized and why?